Okay, no problem.
All right,
That's good.
let's go ahead.
Yes, sir, man. Um, Thank you for coming here for my research plan, and let's dive in. So my name is Han Yu Ling, and then this is my research plan for this semester. My topic is characteristic of magnetic pulsation signature during a specific storm, which will be 23-24 April 2020 storm. And this is this is the agenda for today's discussion. And let's dive in for the motivation. So, what are the magnetic pulsation or this geomagnetic storm related to military? So, if we're thinking about the U.S. military, it's effective in the reason why it's effective is because of the U.S. military are very capable of using this kind of like multi-domain operation, and then in tactical sense, our weapon systems are really emphasized on the accuracy compared to those with the Russians or Chinese military equipment. And when we're doing this multi-domain operations, Army, Navy, Air Force, Space Force, they really depends on a lot of the communications and coordinations, and those are related to the equipment that we're using that's gonna be affected during geomagnetic storm. So those are the list, some of the list examples of what gonna be affected. That's including the radar system, the firefighting radar systems, early warning, missile warning radars, or some of the for the communication affected the high frequency radios, and also GPS receiver. That's what all the weapons is that depends on, and all the satellites communication, and not just for this, but also the space weather, like Gemini storm, also affected the ground, the power systems on the ground. So this is what we call geomagnetic induced currents. That's mainly happened during the geomagnetic storm time. Um, and what happened is you create this kind of current in those power systems that created a power outage. One of the examples was 1989 blackout. So a lot of people affected, and you can imagine what's going to happen if it is during the major operations. So not just the power outage, but we also have the problem with distinguish ability. So there's some paper talking about the nuclear burst EMP can also uh, have the similar signature with this space weather events such as geomagnetic storm or substorm. So let's dig into what's happening in fixes in the background. So geomagnetic storm or substorm are related to um, Danji cycle. And let me show a video real quick about what's happening. So sun, it's like a volcano that have some like explosion. For the sun, they have solar wind or coronal mass ejections. Is this kind of burst, as the video shows. Basically, when it reached toward Earth, under certain conditions, it will open up the Earth magnetic field line, solar wind drag it to the backside, the night side of it, and the magnetic connections happen again at the night side. The plasma it slingshot back to the Earth, and it created this all types of geometric events. So it could be storms and impact on our military operations. Okay. So let's start with dayside reconnection. So in the video, we saw the CME coming out to the Earth. And now, if there's an anti-parallel direction um, of magnetic field line, so the left-hand side, the yellow, is the interplanetary magnetic field from the sun. The right-hand side, the green field line, is Earth magnetic field line. If there's an anti-parallel, what happened is it created the current sheets, and the fixes is the stretch out this current sheets become thinner, thinner. Eventually, uh, this magnetic field line reconfigure and opens out the Earth magnetic field line. Solar wind that drag the Earth magnetic field line to the night side. But at the same time, this plasma inside the CME also going with this magnetic field line. This is called frozen in flux.
Yeah.
So they move together, the plasma and the magnetic field line move together to the night side, and then you create another magnetic reconnection at the night side. Same mechanism here. You have a lot of plasma build up in the night side due to the different rates of reconnection between day side and night side. So the key point is you have a lot of plasma store in the pressure store inside the magnetic tail, and during the expansion phase, what happened is those plasma like rubber band snap.
Yes.
So it eject all the energy back to the Earth along with the magnetic field lines. So this is switch to the topic to what we call a substorm. So substorm and storm within the geometric storm, there might or might not be a substorm. But here's the key points, because substorm usually happens in the high latitude, right? Is associated with the brightening of the aurora, and the what happens is the interaction of this magneto-tail current sheets bring those energetic particle inject into the Earth's ionosphere. And there are three phases during the substorm. There's growth phase, the second is expansion phase, and the recovery phase. So the first phase, the solar wind energy input into the magnetosphere and then store the energy in the magneto-tail. Expansion phase is when the tail current sheet got disrupted, so that all the energy come into the Earth, and then the particles are precipitated into the polar, the high latitude ionosphere, and it enhance all this kind of ionospheric conductivity and the auroral electrojets. So, and the recovery phase is pretty simple, just the disturbance weakening. You don't have new CME or the plasma coming in and to cause these substorms. And the field line current is something that connect between the ionosphere and the magnetosphere. The magnetic flux tube, which also like referred to substorm current wedge. But the key point is there's a connection between magnetosphere and ionosphere. So this is now we're going to talk about the main topic here, magnetic pulsation. This is what we're looking at. So basically, magnetic pulsation is the natural oscillation of the Earth in field lines. When the solar wind interact with the Earth, it causes a lot of magnetic perturbation, and those generate ultra low frequency waves. And when we observe those waves on the ground, and then we call it like magnetic pulsation. And we saw that in we can use ground magnetometers station trying to see if we can solve this magnetic pulsation. And the pulsation actually has a different sources. This can cause by the first of all we call Kelvin-Helmholtz instability. It's basically the velocity difference between the solar wind and the magnetic pulse. So the solar wind is pretty fast coming hitting the magnetic pulse, but then because the velocity difference it create vortices along this the flanks of the magnetic pulse. So thinking about this, you have a wind blowing on the surface of the lake. So what happened is you see the lake have this kind of ripples and the waves, and it kind of transmission down to the deeper of the lake. Same thing happens here, where you have as the picture shows on the left hand side of the picture. This is what exactly what happens. The amplitude of the waves decay away from the surface, and we saw that on ground stations. That's why we can measure saw the pulsation. Now the second one, we have pressure pulses in the solar wind. This is basically the compression from the solar wind dynamic pressure. When the storms happens, the dynamic pressure increase rapidly, and this creates the compression waves, because the whole magnetic pulse got magnetosphere got compressed, and this displacement caused that the ultra low frequency waves. Now the next one is the ion cyclotron waves in the foreshock. So what's basically the foreshock? When the solar wind hits the Earth bow shock, some of the ions are reflected backward, and these backstream ions all collected with the incoming solar winds. So it's creating like a turbulence regions that generates waves. So these waves all drift back to the Earth, and then we saw this signature of those pulsation, those waves, and magnetic activities. Basically, you can see a lot of those things going on at the same time during the geomagnetic storm or substorm. So now, how does this wave propagate to Earth? Is it like a speed of sound, right? We need a media to travel the sound, and we travel like 340 meters per second in the airs. So similar idea, but in the space in the mesosphere, this is the media is governed by Alfvén velocity. This would determine the speed of the pulsation propagates. So basically, Alfvén velocity determined by the strength of your magnetic field strength and the plasma density. So if you have a higher magnetic strength, higher magnetic field strength in the inner magnetosphere, you get a greater Alfvén velocity. And supra-Alfvénic and sub-Alfvénic have different phenomena to different impact to our Earth, and it's very critical that we consider this factor when we're doing the analysis. Next, we're talking about the boundary, the ionosphere boundary. So the main point is that this ultra low frequency wave in this ionosphere will reflect back and forth if the conductivity is high. When the conductivity is low, the waves only partially reflected, and some of them can be transmitted. So next, MHD equations. Those are the background fundamental physics that's important to understand when we trying to doing this kind of project or research. So first of all, the Faraday's law. Faraday's law is the main factor that contribute to the ground-induced currents. When we talk about page 4, we're talking about geomagnetic-induced currents. This is what impact our grid line. 5. So here. So what happened is when your magnetic field got changes by the geomagnetic storm, the change of magnetic field with respect to time would generate a circulating electric field in another direction, and that's fundamentally cause the ground-induced currents that impact our grid line. Also, we have Ampere's law. Ampere's law, you have a current, and this is J, this is a current. So the currents would generate a circulating magnetic field. So why is important? Because when we're doing the analysis on ground magnetometer stations, what the station measure is measuring the magnetic field changes. So we can infer what's happening in the ionosphere or the whole Earth magnetosphere structure, the current structure, using Ampere's law. And the next, we're talking about no divergence for the magnetic field. It's basically talking about the Earth is Earth is closed field lines. This closed field line only break down in the current sheet at magnetotail or the daytime magnetosphere. The second one important thing in Ohm's law in the bond equation is that when we talk about frozen influx, this is where the plasma move with the magnetic field line, and this is the law that governs it. And next, we talking about how scientific society categorize all the magnetic pulsation. So this magnetic pulsation, or they call it ultra low frequency pulsation, can be categorized to two types: the PC type and PI types. PC type is a continuous pulsation, which have a regular form, waveform, and PI pulsation has a irregular shape, and those PC and PI have different frequency range. And as you can see at the table down here, Scientific Society has doing a lot of publication on which type of pulsation has related to which kind of events. And what those papers are saying is PI2 sometimes related to the night side, the substorms, and the PC 3 to 5 correlate to the day side, and the like the compression and those kind of events during day side. But how it's gonna look like, we're gonna see in the later pages. So this is the kind of like an idea, so how it looks like on the ground, on the stations. You have a irregular pulsation, you have a PC type of pulsation. This is just an example. Now,
I'll do that.
this is the plots that we from last semester and this semester we working on. So first of all, let's explain what are those in panels are and what indices we're using. So the top two plots, we use SuperMag, which is the ground magnetometer station all over the world, and trying to tell us some of the story. The first panel is SMR. SMR is a ring current, basically indicator for ring currents, and this is taking the station at the lower latitudes stations and trying to see the ring current. It also, usually is related to geomagnetic storm. The second panel is SMU, SML. It's similar to AU and AL, but just have more station added to it. It's taking the high latitude stations and trying to analysis westward electric jet and eastward electric jet. Basically, it will tell us what the currents pattern looks like, and this is one of the indices that we use for substorms. Now, the third panel is the the third panel is the magnetic perturbation in a single station in so for this example we use in Canada ground magnetometer stations. So the first of all we doing the we found the quiet time or average out all the magnetic field strength, and then trying to see in each time how is it gonna change. So basically magnetic perturbations, and the bottom panel is basically we're trying to correlate the signal power with oscillation amplitude to see, what cause what in this in the top panels what caused the signal power went up or weakened. So the yellow color means the signal power is strong, and the the dark blue means the signal strength is weak. So what we can see, what we found in last semester is that the ultra low frequency waves, what we call broadband wave power, is all the frequency range. Sorry, I need to orange you to the wider y-axis. The y-axis is stored by frequency range. So PC5 at the bottom had the lowest frequency, and the top is PC3 and PI2, which have a higher frequency range. What we saw is all different type of pulsation, all illuminated during a certain time period. This is called the broadband ultra low frequency waves. And what the scientists, the other papers are talking about is that the during geomagnetic storm, we usually see this broadband phenomenon because there's a lot of different turbulence going on and illuminated all different stuff. In scientific way to say that the ultra low frequency interact with the energetic particle, right? In Earth inner magnetosphere, the particle usually do three things. they do gyro motion or bounce motion and drift motion. And what happened is the ultra low frequency particle interact with um, uh, those drift motion and bounce motion, and it cause the particle to accelerate or loss. And then they categorize the different types of interaction. They're diffusive interaction and resonant interaction. Diffusive interaction is basically a random motion. There are turbulence going on and cause ultra low frequency wave to interact randomly with the local plasma, and the result in oscillation or loss the plasma. That's why we saw all the frequency range is kind of lights illuminated at the same time. The resonant interaction works better during quiet time. This is just a single ULF wave with appropriate structure exchange energy with ions and electrons through the drift and drift bounce motions. So you can see on the right hand during kind of like a quiet time, you see little illumination at certain pulsation type. And their paper saying that the efficiency of the discrete wave particle interaction are more efficient than the broadband interaction. That means that we cannot ignore the effect of discrete ultra low frequency, meaning that we might still have able to see some of the stuff going on even during geometric storm.
Can I ask a quick question for clarification?
Right.
So you talked
Sure.
about basically two categories, these discrete ULF waves like PC3, PI2, and then you're also talking about broadband. Just roughly speaking, what would the difference be between those two as they would show up on that bottom plot?
Yes, sir. So discrete ULF wave is mean that like the only a single ultra low frequency range will light up. So the it's not instead of like broadband will be every uh illumination in every single frequency range. So you can see down here all the way to 25 megahertz. They all illuminate at the same time. This is called the
Gotcha.
broadband. But then the discrete ULF will be just a certain frequency range will illuminate it.
Gotcha. Okay. Yep. Thank you.
Sure. So let's continue with this wave particle interaction. So this is the paper from Murphy talking about ultra low frequency wave and the thing that we're just talking about. This graph is a probability distribution of the discrete ultra low frequency, and the right side is the broadband ultra low frequency wave. And you can see, so during geometric storm time, we usually see something like on the right hand side. This donut shape is filled. This donut stuff in the inner donuts is the I believe is the lower frequency, and then the outer donuts is the higher frequency range. So you can see different frequency has illuminated at different time. It's really confusing and like have a lot of the random stuff going on. And that's what we saw during the geometric storm time. The discrete ULF on the other hand side, you can pretty much see, PI2 pulsation illuminated during 2 o'clock to 6 o'clock Manila local time. So it's very you can do an analysis on this, but on the right hand side during storm time it's really hard to. It's just the key point is that it's difficult to analyze the ultra low frequency during storm time. So now let's take a break and then shift to another topic talking about. This is just some of the side idea that I have on how to determine a substorm onset. So the current method, there are two main things that me and Dr. Durr is looking at. Is the one is called Neuberger-Gerloff substorm onset criteria. The another one is Solfi paper. So basically, substorm onsets usually associate with this DP1 current system where you have energetic particle at the night side and then inject into the night sector of your ionosphere, and this create a substone electric jet. And then the enhancement in the night side is what captured by the SML indices. SML is basically measure of westward electric jet, which is this red line here. And the SMU is basically an indice that measure westward electric jets, which we'll use usually to check if the current pattern is DP2. So DP2 current is the global enhancement, is usually not associated with the soft storm. So what Newark Gerloff paper was using SML, and in every minute there's a standard that you need to drop at least 15 nanotesla, and second minute you need to drop at least 30 nanotesla, and the remaining 26 minutes you need to remaining at least below this 100 nanotesla, which means that you need to have a certain rate of change of your westward electric jet strength. And this and the Solfi paper was using similar, but Solfi paper also compare with the SMU to separate DP1 and DP2 current systems. But they are also downside of it because it's not 100% accurate. It does only have, I don't remember the number, but it was 59% accuracy. But what happened with the current substance onset standard, me personally, my idea was when I look at this graph, this is the graph that we make using SMU and SML indices, and this is the day side, 12 o'clock, and the MLT, and 00 is the night side. And to separate the DP1 and DP2 current system, what you need is to see if there's a SML, westward electric jets enhancement during the nighttime sector. And if there is, there might be a chance that it's a global enhancement because if it's a global enhancement, then everything else, every sector will have enhanced as well. So we need to separate that, and my suggestion is using SMU LT, SML LT index. So SML LT is similar to SML, but it just like this graph, it has in each hour sector, MLT sector, it has its own measurement. So you can see instead of just saw the whole SML drop, you also see like where exactly is the effect. So you can see here is about like 0.3, 0.6 at the night side. And we will continue with this later on, but it's just a side idea. And then sometimes I notice is that the Solfi paper that doesn't address is that there's SML LT global enhancement, but according to the Solfi standard, it will identify this as a DP1 structure, but in reality, it might be due to the compression of the solar wind that caused the entire SML LT to drop to enhance, but the SMU still remaining the same. And this is the future plan. Sorry, this is not 100% correct. I'll need to correct this, but basically what we continue doing is today is our research plan. We will have our IPR 1 and 2, and the final out brief at the end of the semester. The the research paper that we did from last year with other cadets, we will have to publish in the end of this week, and the magnetic pulsation paper that I'm working on, I will continue to finish out the paper, and then we will have to do some of the literature review, either on the introduction on the space physics or on the daily basis with the JGU paper. And these are the reference that we use for the brief. And depending on any questions, this is my research plan.
All right, outstanding. Okay, so I guess I have very few kind of big picture comments. And then we'll, call in others who may have more. I mean, there was a lot of information in here. You explained a lot of things well, but I think my assessment is that you tried to explain too much so that it's a bit hard for the audience to know what exactly to focus on. You have a sense of what the more and less important points are here for the main project, but many people will not. I mean, some of this is just a challenge of you're trying to explain one project and then you jump to the very interesting. I think the coolest part here was your substorm onset method idea. Let's see. For that method, so I'm trying to make sure I understand the idea. Is the basic idea that other methods have this deficit of not seeing the local time or latitude distribution of current systems? So if you just use these SMU, SML indices without the local time fine-grained stuff, you're going to capture false positives and false negatives. Like non-substorms will be called substorms, and so on.
Exactly. Okay. Yes, sir. That's the idea.
So I think that's definitely a useful thing for us to pursue. I mean, depending on how you reprioritize your efforts, and we'll see if others agree, I think it might be good to just pick one project for the IPR discussion so that it's easier to know what specifically to highlight. I also think on slide 21, here, I think it would have been nice to point to the DP1 and indicate for the audience that that's the ionospheric leg of the substorm current wedge you mentioned before.
Right. Yes.
Because otherwise they won't understand that the DP2 thing is just not a substorm, which is one of your main points. I also think an explanation of indices is definitely important for your presentation because you use them heavily.
Yes, sir.
And then a last comment for improvement, I would say the Gantt chart is somewhat incomplete. I think task break.
Yeah. Yes, sir.
And you did mention that, but yeah, task breakdown should probably be more focused on the breakdown of scientific tasks than the sections of the paper. And also, the green and blue lines, you should basically have one of them for every row, is my understanding of a Gantt chart.
Right.
All right, so and that's all I have. I mean, I'll go through and nitpick all different little detailed stuff with you later, of course. But let's see, Colonel Laux, Dr. Grazier, either one of you jump in.
Could we go back to plot or to slide 22, page 22? The windrows diagram. Yeah, that one.
This one. Yes, sir.
Yeah. So you're saying these indices have some predictive value. Yes.
Yes, sir. So basically, if we see, nice, this is just a one picture. So what we made is every 5 minutes we have one of the picture like this, and you can see the evolution of the SML and SMU. And you definitely can see when the nighttime this went crazy, went illuminated, then you can infer that as maybe like a substorm onset. But we need to be careful and to make analysis. But yes, this is will be like a way to detect the substorm onset.
Okay, so you need this is like one slice. In other words, you need several of these.
Right.
This is
There'll
okay.
be a video basically, but I just choose a one picture as an example because yeah, I this is just an idea basically.
Okay, I understand. Okay, I just wanted to make it clear. So, in other words, but you do need the whole. You need more than one
Yes, sir.
Okay. Um, Here's an idea for your presentation. There are tools where you can actually take several of these and make an animated GIF from it.
Yes, sir.
That's just a recommendation. You can turn this into an animation fairly easily, and then you can go more into the detail into how it's predictive and you at what point is this telling me, you know, that there's a likelihood of a storm. Anyway, that's just a suggestion. I know you have plenty of other things on there to do, but that would I'm just saying this might help you make your point or clarify your point and
Yes, sir.
how
That's a
it's
great idea.
predictive. Okay.
Right. Yes, sir.
Can I just, because you mentioned that, can I just jump in with one minor thing? In addition to the video, you might want to just when you know, whether you show a video or one panel, explain how you in your head are translating between this picture and the different strengths of eastward and westward currents. So like when I look at this, I know how to interpret it because we've discussed it many times.
Right.
But basically the idea is translate between, okay, SML, so you've got strong eastward currents where the orange bars are large, and then kind of like a balance of eastward and westward on the dusk side, I guess, right? I think I'm interpreting that right. I mean, you're the one that made the... But, you know, saying something like that will translate it into something people understand better, pictures of arrows. Yeah.
And it will be even better if we can show like I think animation would definitely help better to saw that global enhancement, to see all this kind of blue and red enhanced, for better understand how to distinguish between two different current patterns. That's definitely a great suggestion. Yes, sir.
All right. Any more, Colonel Laux?
Is there Colonel Laux?
And I don't know if Dr. Grazer was done. I just kind of jumped in.
Is Colonel Laux can use the speaker, so. Sorry, your mic is muted.
Sorry. All right. So I'll just, you know, briefly comment what she said. Impressed with how far your explanations have developed, etc. Totally second that. I think she's agreeing with me here. There was a lot of information, so that I think it's just a challenge for anyone with this much information to not skip some explanation and then speak over people's heads. Yeah. So I agree with the point of eliminating some of the distracting things, mainly in that, you know, for example, you're talking about the different drift motion, bounce motion, this kind of stuff. The explanation was fine, but it's so many steps away from the main point that people aren't going to have any sense whether that's more important than the pulsations, for example. So yeah, for like a super long detailed presentation, you might want to say that. But for something like a research plan, you really want to keep it to like the very fundamentals.
Yes, sir.
I don't know. Did I finish what she said? Yeah. All right. And I don't know if I interrupted Dr. Grazier.
Well, I do want to add one other thing. I agree that it was a fabulous talk, and one of the things I also wanted to point out is I didn't want to leave with the only thing that I said having been it seemed like a criticism, because this is grad school level work. I just wanted to say that. So well done.
Thank you, sir.
Yeah, for sure. I mean, I should say, like, I'm this substorm onset criterion. I should stress to everyone, this was, of course, floating in the air in our discussions, but the idea is totally Hanyu. So that's a very insightful thought. Implementation is certainly going to have some challenges along the way, but I think it's worth pursuing. I think it would. I think you're correct in your intuition that it would enhance our likelihood of getting substorm onset detections right in a greater fraction of the cases. Yeah.
Yes, sir.
Okay, well, prediction. Okay, what this potentially leads to is, like a watch or warning, like to do with tornadoes. So you could, as you refine the model, you start implementing warnings when you are more confident, but you can have watches like we have geomagnetic storm watches, because we know we've seen an event happens that we know is going to lead to very likely to something. Well, as you refine this, this could be again, a kind of a watch is, well, we've seen this event. We know with X likelihood that there is going to be a substorm.
Yes, sir.
I'm just throwing it out there for you to use or not as you see fit.
Yes, sir. Thank you very much.
Yeah, that's great. And then
Great.
in addition to, there's going to be a substorm, maybe given what we know about different current systems, since this allows insight to that the other indices don't, you could say something like, oh, we have a DP2 coming in, therefore power grid outages are more likely, as opposed to like GPS scintillation or something like that. Yeah, that's a great idea. All right, and I know Ahmad is joining us here. Ahmad, do you have any questions or? Oh, should I? I'm sorry, I called you Ahmad. Should I call you Al? I'm not sure what your preferred.
Either works, sir, but
Okay.
I don't think I have I don't think I have any questions right now. I feel like I need to kind of understand the topic a little bit more to be able to understand what's happening overall to start actually asking relevant questions, if that makes sense.
Yeah, sorry. I have to apologize. Yeah, I know that the topic is jumping around too, because I have some side ideas like this and my main stuff, and it's everything kind of like tangle out the things. I can make I should make it like a presentation more like in a way that most people can follow it at the same time. We only have like 40 minutes, so I know it's too much like kind of information that like blows your head. I remember last year I was trying to join the research group. I couldn't understand anything as well. And I think me as a presenter, I can make it way better to in a way that people can track in without losing, because of too much information in it.
Yeah.
Right, yeah, I understand, but I mean, I came in last minute. I think this it was more directed towards everyone else in here who
Yeah, that's
probably have a way better understanding of the topic. So I really do not blame you. Since they understand it more, so it's more tailored towards them. I mean, I still have time to understand it. We're not in a rush or anything.
Yeah, so I think what we'll do is we'll have you join a meeting with me and Han Yu, and we'll all discuss more of the fundamental stuff. And yeah, as you said, I think Han Yu had the PowerPoint mostly made, and then you know, we had like one day after hearing that you were going to join. So, with that in mind for next time, you know, you will know more coming in, and we'll have more time to make it for that audience. Yeah. All right.
Okay,
So
perfect. I'm excited to meet at that time.
yeah. So I guess Ahmad, Al, which do you prefer? I mean, if I'm gonna use one, I'm happy to use either.
Uh, I do not mind either. Usually people here call me Al since it's easier.
Gotcha.
So I can do that one, sir.
All right, sounds good. So, do you want to
Yes.
stay on with me and Hanyu briefly, and we'll discuss setting up a meeting time, something like this?
Yes, we could do that right now.
All right.
Sure.
And if you have to go in
Th-
10 minutes or something, you know, whenever you're done, that's fine.
Thank you, sir, man. Yes.
All right. Thanks, everyone. See, I'm gonna stay on with Hanyu and Al, and we'll discuss briefly.